Imagine traveling to another planet, carrying with you the single most important tool of your entire mission. A drill capable of extracting the one piece of evidence that could prove life has existed somewhere beyond Earth. Now imagine watching that tool succeed perfectly, follow every instruction exactly as programmed, seal its sample away precisely as designed, only to discover afterward that the sample itself had simply vanished, turned to dust between the moment it was collected and the moment anyone checked. This isn't science fiction. It happened on Mars in the summer of 2021 to NASA's Perseverance rover, and the story of how that failure unfolded and what the mission team did next says as much about the reality of exploring another planet as any successful discovery ever could. Perseverance touched down in Jezero Crater in February 2021, and unlike every rover NASA had sent to Mars before it, its mission wasn't simply to search for conditions that might once have supported life. It was built to search for direct physical evidence that life had actually existed there. Fossilized traces of ancient microorganisms embedded in rock, hard proof rather than favorable circumstantial conditions. But that hunt didn't begin the moment Perseverance's wheels touched Martian soil. For its first 4 months on the planet, the rover stayed relatively close to its landing site, testing its own systems and assisting an entirely separate experimental aircraft. The small Ingenuity helicopter, with its own historic flights, the first powered flight ever achieved on another world. Only once that initial phase wrapped up did Perseverance actually set out on June 1st, 2021, to begin the job it had traveled roughly 300 million miles to do. The destination was Jezero Crater itself, a genuinely fascinating location chosen with great care. Millions of years ago, a massive impact carved this crater into the Martian surface, hundreds of meters deep and roughly 25 miles across. Under the very different climate conditions that existed on ancient Mars, that crater gradually filled with water, becoming an enormous lake, hence its name, which in several Slavic languages simply means lake. Rivers once flowed into this basin, carving valleys through the surrounding terrain and depositing massive deltas of silt and sediment where they emptied into the water. If life ever existed on Mars, and if it behaved anything like life does here on Earth, a location like this, an ancient lakebed fed by rivers carrying sediment and nutrients, would represent one of the most promising possible environments for it to have emerged and persisted. Today, Mars is a cold, barren, apparently lifeless world, meaning whatever evidence Perseverance might find wouldn't be obvious or immediately visible. Any organism that once lived in Jezero's ancient lake would have died, sunk to the lakebed, and gradually been buried under layer after layer of silt, eventually compressed into solid rock, exactly the kind of place where microscopic fossils might survive, hidden for millions of years. To retrieve that kind of evidence, Perseverance came equipped with a genuinely sophisticated toolkit. A drill mounted on a robotic arm roughly 6.5 feet long, capable of either abrading away a rock's weathered outer surface to reveal fresh material underneath, or coring out a cylindrical sample roughly the size of a piece of chalk and sealing it inside an airtight collection tube. Working alongside instruments like Sherlock, an ultraviolet spectrometer, and Pixel, an X-ray fluorescence spectrometer, the rover had everything it needed to identify, photograph, and carefully collect promising rock samples for eventual return to Earth. Sherlock works by firing a focused ultraviolet laser at a rock's surface and analyzing the resulting fluorescence, a technique capable of detecting specific organic molecules and mineral signatures associated with ancient microbial life, effectively letting scientists scan a rock for promising chemical fingerprints before ever committing a precious drill attempt to it. Pixel complements that approach by mapping the fine-scale elemental composition of a target surface, building up a detailed chemical map that can reveal subtle textures and mineral boundaries invisible to the naked eye, the kind of structure that sedimentary rock formed in ancient water might preserve. Together, these instruments let the mission team build a genuinely informed picture of a candidate rock's history and potential before ever risking one of the rover's limited sample tubes on it. This entire approach reflects a hard lesson learned from decades of planetary exploration. Samples collected on Mars, however carefully chosen, are ultimately only as valuable as the science instruments eventually used to study them, and Mars rovers, however sophisticated, simply can't match the precision and depth of analysis available in a proper laboratory back on Earth. That's precisely why Perseverance's mission was designed from the outset not as a standalone sample analysis effort, but as the first stage of an ambitious, multi-mission sample return campaign, one that will eventually require additional spacecraft to physically retrieve these sealed tubes from the Martian surface and carry them home, a campaign representing one of the most logistically complex efforts NASA and its international partners have ever attempted. Every core Perseverance successfully collects and seals today is, in that sense, a kind of promise to future scientists, an artifact patiently waiting years, possibly decades, for the technology and funding needed to finally bring it home and unlock whatever secrets it holds. But those samples had to be chosen with real discipline. Perseverance carries just over 40 sample tubes for the entire mission, a genuinely limited resource given the scale of Jezero Crater and the years the rover is expected to operate. Simply drilling into whatever happened to be closest to the landing site would have been an enormous waste of that limited capacity. Instead, mission scientists directed Perseverance to travel south from its touchdown location, a site named Octavia E. Butler Landing, after the celebrated science fiction author, toward a geologically promising region nicknamed the Crater Floor Fractured Rough, an area whose rock layers were expected to offer real insight into Jezero's ancient history and, hopefully, the strongest possible candidates for evidence of past life. That destination sat barely more than half a mile from Perseverance's landing site, and yet the journey there took nearly 60 days. This wasn't a matter of the rover moving carelessly slowly out of excessive caution. It reflects the genuine difficulty of driving across terrain nobody has ever physically traversed before. Mars's surface near Jezero is scattered with rocks of every size, and Perseverance, with wheels just under 21 inches across, can only safely roll over obstacles up to a certain height before risking damage. Soft terrain poses an equally serious danger. An earlier Mars rover, Spirit, met its effective end after becoming permanently stuck in a patch of loose sand it couldn't escape. Choosing a safe path forward means threading a careful line between ground that's too rocky and ground that's too soft. And for years, that kind of route planning had to be worked out entirely by human controllers back on Earth, communicating with the rover across a radio delay that averages around 20 minutes each way, an agonizingly slow feedback loop for real-time obstacle navigation. Perseverance, however, arrived with a genuine technological upgrade over its predecessors, an onboard AI system called AutoNav, capable of mapping its immediate surroundings and independently plotting the safest available path forward, adjusting its route on the fly as it drives, without needing to stop and wait for new instructions from Earth for every single obstacle. Human mission planners still set the overall destination and reviewed the rover's progress, but this added autonomy let Perseverance travel roughly 6 times faster, on average, than earlier rovers like Curiosity. Its resulting top speed works out to an almost comically modest 0.2 kilometers per hour, genuinely still no faster than a slow, careful walk, but a substantial improvement in a field where every extra bit of ground covered translates directly into more science actually accomplished. By July 20th, 2021, Perseverance had successfully navigated its way to the crater floor fractured rough. Mission scientists proceeded carefully, first testing the rover's abrating function rather than its full coring drill on a flat paving stone-like rock the team nicknamed Guillaume. The abrasion attempt worked exactly as intended, grinding away the weathered surface layer to expose fresh rock underneath, giving scientists their first real look at the grain size, texture, and chemical composition of the stone Perseverance had been driving across. That data helped researchers begin distinguishing between sedimentary rock, the kind most likely to preserve fossilized remains, and igneous rock, formed instead from cooled volcanic material and far less useful for the mission's core scientific goal. What that initial test revealed was encouraging enough that the team moved forward with genuine confidence. On August 6, 2021, scientists selected a new target rock, nicknamed Rubion, for Perseverance's very first actual attempt at collecting a sealed core sample, the real objective of the entire mission. Because of the time difference between Mars operations and the mission team's home base, more than 90 engineers and scientists gathered online at 2 a.m. Pacific time to witness the results in real time. The drilling itself went beautifully. Perseverance cored down to its programmed depth of nearly 3 inches, exactly as planned, captured photographic confirmation of the hole afterward, and appeared, by every available measurement, to have succeeded completely. Over roughly the next 6 hours, the rover carefully extracted the core, deposited it into one of its collection tubes, and transferred that tube to its onboard processing system, called the Adaptive Caching Assembly, before finally sealing it inside long-term storage. Given how critical it is that absolutely no contamination reaches these samples, the entire process is intentionally slow, methodical, and heavily monitored at every stage. Everything appeared to have gone exactly right. The scientists watching celebrated what looked like a flawless first attempt. Then more telemetry came through and the celebration stopped cold. The sealed sample tube, according to onboard weight sensors, was empty. Confusion set in immediately. Because Perseverance only carries a limited number of cameras and can't feasibly photograph every single second of every operation it performs, mission scientists had to rely largely on the rover having correctly followed its programmed instructions, cross-checked against whatever sensor data was actually available, and that data told a genuinely puzzling story. Perseverance appeared to have executed every step of the collection process exactly as commanded, and yet the tube's weight sensor showed no added mass at all, meaning, as far as the instruments could tell, there was simply no rock core inside it. engineers had the rover drive backward and photograph the ground between its own tracks, checking for any sign that a core sample might have been accidentally dropped somewhere along the way. Nothing was there. Eventually, after careful analysis, mission scientists arrived at a genuinely bittersweet explanation. Perseverance itself hadn't malfunctioned in any way. Every mechanical step had worked precisely as engineered. The failure was entirely due to the rock itself. Rubion turned out to be so unusually crumbly and structurally weak that the moment the rover attempted to lift the freshly drilled core, it simply disintegrated into dust, far too fine and fragmented for the collection mechanism to actually gather and store. Before launch, engineers had tested Perseverance's drilling and coring system on roughly 100 different rock samples back on Earth, and not one of them had ever behaved this way. Every prior test rock had cored successfully. In one sense, this was genuinely reassuring news. It definitively confirmed the rover's hardware wasn't broken or malfunctioning in any way. But it also introduced a troubling new question that nobody could immediately answer. If a completely ordinary drilling attempt could fail simply because a particular rock happened to be unusually fragile, how many other rocks scattered across Jezero Crater might present the exact same problem? Was this a fluke or a genuine pattern the mission would keep running into? NASA had no intention of giving up after a single setback. The team reasoned that Rubion's extreme fragility likely reflected unusually severe weathering specific to that particular location, and that sturdier rock elsewhere in the crater might hold together far better under the same drilling process. Scanning the surrounding terrain, Perseverance's cameras identified a promising ridge roughly 160 yards away, visibly different in both texture and structure from the flat, crumbly paving stone terrain that had failed the first attempt. Because these new rocks rose up from the surrounding landscape rather than lying flat and weathered, scientists reasoned they were likely composed of considerably tougher material, having actively resisted erosion rather than simply eroding down into loose, crumbly stone. The team nicknamed this new target Citadel, French for citadel or fortress, a name that reflected genuine hope this attempt would prove considerably more solid than the last. Perseverance carefully maneuvered itself into position at the ridge and prepared for its second serious attempt at collecting a sample. On September 1st, 2021, almost exactly a month after the disappointing Rubion attempt, the mission team gathered once again to watch Perseverance try a second time. That month-long gap wasn't wasted time or excessive caution for its own sake. Every available scrap of data from the first failure had to be carefully reviewed, every subsequent decision deliberated and cross-checked before committing to another attempt. Space missions of this precision leave essentially nothing to chance, and each individual drilling attempt represents genuine, non-renewable resources: time, limited sample tubes, and irreplaceable drill bit wear, none of which the mission could afford to squander carelessly. This time, Perseverance's drill successfully extracted a core roughly 2.5 inches long, and in what genuinely reads like a small, wry lesson learned from the earlier failure, mission engineers had the rover perform an additional, previously unplanned step before sealing the tube, photographing the core directly, visually confirming to everyone monitoring from Earth that an actual physical sample really was sitting inside the collection mechanism this time, rather than relying purely on indirect sensor readings that had proven misleading before. And this time, the photograph confirmed it unambiguously. There, held securely, was genuine Martian rock. The relief among the mission team must have been immense. Data confirmed Perseverance had successfully transferred the core, nicknamed Mondenier, into secure long-term storage, ready and waiting for an eventual future mission to physically retrieve it and carry it back to Earth, where far more sophisticated laboratory instruments than anything a rover could carry would finally have the chance to analyze it in genuine detail. Riding that momentum, and perhaps understandably eager to be absolutely certain after the earlier disappointment, Perseverance collected a second core sample from the very same rock formation that same day, giving the mission an additional backup sample from a location scientists now had real confidence in. None of this, it's worth being completely clear, proves that life ever existed on Mars. These samples still await return to Earth and detailed laboratory analysis, using instruments far more sensitive than anything currently sitting on the Martian surface. What the successful Mondenier core actually represents is something more modest, and in some ways more honest about how real scientific exploration actually works. A single, hard-won step forward, preceded by a genuine failure that could easily have derailed months of careful planning, resolved not through some dramatic technological fix, but through patient analysis, a willingness to learn from an unexpected setback, and a simple decision to add one more verification step before declaring victory next time. This story, more than any single successful drilling operation, captures something essential about what exploring another planet actually involves. It isn't a clean, uninterrupted sequence of triumphant discoveries. It's careful engineering meeting genuine, unpredictable uncertainty. A rover following its programming flawlessly, only to be undone by a rock's unexpected fragility, a team confronting a real failure with methodical persistence rather than panic, and a mission ultimately succeeding, not despite that early setback, but partly because of the lesson it forced everyone involved to learn. It's worth remembering just how unforgiving the environment actually is for troubleshooting a problem like this. There's no possibility of sending a technician to physically inspect the drill, no way to simply pick up the rover and shake out whatever went wrong. Every diagnosis has to be built entirely from indirect evidence, sensor readings, camera angles chosen weeks in advance, and careful physical reasoning about what could plausibly explain a specific, unexpected result, all filtered through a communication delay that turns even a simple question into an hours-long conversation. The fact that a team of engineers, working purely from telemetry and photographs taken tens of millions of miles away, could correctly diagnose that a rock had simply crumbled to dust rather than assuming a mechanical failure in a multi-billion-dollar piece of hardware says as much about the rigor of modern mission engineering as any successful sample collection ever could. Perseverance is still out there today, years into its mission, continuing to fill its remaining sample tubes one careful attempt at a time, each one representing a small, patient step closer to answering one of humanity's oldest and most profound questions: whether we have ever truly been alone. And somewhere in a secure storage cache on the Martian surface right now, Montagnier and its companion core sit waiting, sealed against contamination, patient in a way only geology can be, for the day a future spacecraft finally arrives to carry them home and put them under a microscope no rover could ever carry.